Hello, everyone, and welcome to tinyML Talks. My name is Evgeny Gusev. I'm from Qualcomm in the Bay Area, and we also have a guest from California today, from San Diego, Dan Riedler from Silicon Labs. So the title of his presentation will be Create a Voice-Controlled Pac-Man video game with Silicon Labs. So before we start, it is my privilege to acknowledge our sponsors and strategic partners. It's AZIP, Analog Devices, Aeon Devices, ARM, DeepLight, H-Impulse, EMSA, PhotoHub, Greenwaves, Grovity Inc., IBM, Imagimob, ITMIS, Clickertech, Microsoft, Nota, .ai, NXP, OctoML, Prophecy, Kixo, Qualcomm, Reality, .ai, Rixen, Renaissance, SAP, Seed Studio, SenseML, Silicon Labs, Sony Semiconductors, ST Microelectronics, StreamAnalyze, Synaptics, SynSense, Syntiant, and TDK. Just a reminder, a couple of reminders, tinyML communities growing fast. You can join meetup groups. There are 46 groups in 37 countries now, close to 12,000 people. So there is a QR code on the left, or there is quite active tinyML community on LinkedIn, over 10,000 people there. So you're very welcome to join them. To get more updates and news and to be part of this community. The tinyML YouTube channel is also quite active with close to 8,000 subscribers and nearly 500 videos. You can subscribe to this channel now, and this video is going to be available on YouTube this week, and the link and the QR code is there as well. And at this point, it is my pleasure to introduce our today's speaker. It's Dan Riedler. He is a principal machine learning software architect at Silicon Labs. Silicon Labs is a tinyML partner company. He's been with the company for about 5 years and more than 10 years in the industry. And for the past several years, he's been helping with Silicon Labs with machine learning technologies, and as part of the machine learning enablement, he was the primary contributor to the Silicon Labs machine learning toolkit, and that's what he'll be sharing today. So Dan, the stage is yours.
So as I said, I'm Dan Riedler. I'm a software engineer here at Silicon Labs, and today I'll be describing how to create a voice-controlled Pac-Man video game. For today's presentation, I'll first go over what Silicon Labs has to offer in the ways of machine learning. I'll then provide a live demonstration of the Pac-Man video game. From there, I'll describe the Silicon Labs Machine Learning Toolkit, or MLTK, which was used to create this demonstration that you'll see today. From there, I will describe how to create a keyword spotting model using the MLTK. And then I'll go into more details on how to actually deploy the machine learning model to an embedded device. Then we'll wrap up with a summary and then Q&A at the end. So first, a bit about what Silicon Labs has to offer in the ways of machine learning. Silicon Labs has the industry's widest portfolio of wireless solutions. We offer Bluetooth, Zigbee, Z-Wave, and a whole slew of other wireless protocols. We also feature an integrated machine learning hardware accelerator in our MG24 chips. The hardware accelerator offers up to 8 times faster inference times at 1/6 the energy. This can greatly help to reduce design complexity and also reduce inference latency. Silicon Labs offers a wide range of development tools and solutions, from explorers all the way up to expert developers, which can help to expedite the development of machine learning applications. We partner with Edge Impulse, SenseML, Sensory, Micro AI, who can help to handle a lot of the hurdles that come up when creating a machine learning application. We feature the TensorFlow Lite micro software stack in our Silicon Labs Gecko SDK. If you're not familiar, our Gecko SDK is our software suite that's used to develop for our chips. We also offer the Silicon Labs Machine Learning Toolkit, or the MLTK. This provides complete control and flexibility for expert developers. It's completely open sourced on GitHub, and it allows for complete control of developing the machine learning model and the application on an embedded device. So in the end, we want our customers to be able to choose the tool that works best for them. They can either partner with one of our third parties who will help them to get to the solution faster by solving a lot of the problems they might occur when creating an ML application, or they can have more control using the MLTK. So let's jump right into the demo. First describe the hardware and software used to create this demo, and then I'll provide a live demonstration of the voice-controlled Pac-Man video game. So first, a bit about the hardware. This demo was created using the DK2601B development kit. This features the XG24 wireless SoC with multi-protocol radio, including Bluetooth Low Energy, or BLE. The XG24 features the Cortex M33, which has 256K of RAM, 1.5 megs of flash, and it runs at 80 megahertz. The XG24 also features a machine learning hardware accelerator. So this will allow for the machine learning model to execute faster on the XG24. And also the 2601 dev kit features an I2S microphone, which will be used for this demo. So for software, the Silicon Labs Machine Learning Toolkit, or MLTK again, features a Bluetooth Low Energy audio classifier example app, and this is what's used for this demo. The app was created using the Gecko SDK with its integrated BLE stack. It also uses TensorFlow Lite Micro, which features custom kernels that are optimized for the machine learning hardware accelerator that comes with the XG24. And then the machine learning model itself was created using the MLTK's model training scripts, model profiler, and model evaluation utilities, which I'll get into a bit later in this presentation. The demo also uses a web page. The web page is just a standard web app that was slightly modified to use Bluetooth Low Energy so it can talk to the dev board. So here's a very rough system overview of the demo. On the left, we have a user saying one of the supported keywords, left, right, up, down, stop, or go, which is captured by the dev board's microphone. The buffered audio in the XG24 is then sent to the machine learning model that's executing on the XG24. The machine learning model reads in the audio and classifies it. And if a keyword's detected, the detected keyword is sent to the web page via Bluetooth Low Energy. So if you say the word left, the machine learning detects that it's the word left and sends it to via Bluetooth to the web page, and the Pac-Man goes left. And likewise, right, up, down, stop, and go. The web page itself is publicly available. It's at mltk-pacman.web.app. Anybody can, it's out there live today. To use this demo, you need a development board. There's a link you can see here on the slide. And then full documentation for how this demo is created is available on the Silicon Labs MLTK's documentation website. There's a link to this as well. I'd like to note that this presentation aims to be a little bit more high level, just covering some of the higher level concepts used for this demo. For more thorough details on how to actually create the machine learning model and deploy it to the device, please see the tutorial on the MLTK's docs website. So, without further ado, let's jump right into the demo. So here's the live web page, mltk-pacman.web.app. There's a few installation steps to get started with a demo. First, we need to obtain our 2601 dev kit, which you can get on our Scilab's website. Next, we need to install the JLink driver. This is required so that we can actually talk to the dev board and flash its firmware. The JLink driver can either be installed by Silicon Labs Simplicity Studio, which is our IDE used for firmware development, or you can just directly download the JLink driver from the Seeger website, which is also linked. Next, we need to download the firmware for the dev board. This is the actual app that has the machine learning model in it and TensorFlow Lite Micro and all the other software required to capture the audio and classify it and send it via Bluetooth Low Energy to the web page. So we download our firmware image. Next, we download the Silicon Labs Commander utility. This is just a simple utility to flash the firmware image to the dev board. So once we use Commander to flash the firmware image, the firmware will automatically boot up and begin broadcasting via Bluetooth Low Energy. Once the app's running and Bluetooth's ready to go, which that will start automatically, we can click on this link here, and this will allow the web page to connect to the dev board. So I'm going to go ahead and share the sound here so you can hear some of the Pac-Man audio. So now, click here, we can see that the web page is searching for Bluetooth devices. It found the dev board, MLTK keyword spotting. So if I click pair with it, this will allow the web page to talk to the dev board by Bluetooth Low Energy. And so that way, when I say a keyword and the machine learning detects the keyword, it'll send it to this web page via Bluetooth, and then we can update and move the Pac-Man around. So I'm going to go ahead and pair now. So now we're ready to go. The keywords that I speak will be captured by the dev board's microphone. The machine learning running on the MG24 will classify the audio, and the detected keyword will then be sent to this web page, and the web page will do something with the detected keyword. So let's go ahead and start it up. Go. Right. Down. Left. Down. Right. Up. Left. Right. Down. Left. Up. Right. Up. Left, down, right, down, right, down, left. Oh, there you go. Stop. Stop. So you can see it's fairly responsive. The keywords I detected were fairly responsive. It was moving the Pac-Man around for the most part. Also like to draw your attention to the bottom left here. This provides a command log. So all the commands that I said during this demo are logged here. And then also, so we have the keyword, the keyword that was detected, and then the confidence. This is the confidence of the machine learning model. So when the machine learning model tries to detect a keyword, the output is just a probability of which keywords detected. And you can see this is the confidence that the given keyword is what it is. So the machine learning model for this particular down here was about 99% certain that the actual keyword was down. So I would also like to bring your attention to the links below here. Full documentation for this website and how it was created is available on the Silicon Labs MLTK documentation. So you can go into far more thorough detail on how to create this demo, how it was created using the machine learning toolkit on the Scilab's MLTK documentation website. So I'll get into the latency for the model, but just to answer it quickly, it was 82.8 milliseconds approximately, just to run the inference. And then there's also latency to generate a spectrogram, which I thoroughly go into those details in a bit here. So now that we have our demo, now that we saw the demo and saw it working, it was created using the Silicon Labs Machine Learning Toolkit. So what exactly is the MLTK? Well, the Machine Learning Toolkit, or the MLTK, is a collection of scripts and utilities to aid the development of machine learning models for Silicon Labs embedded MCUs. It features a command line interface, which allows for executing the various machine learning model development tasks, including profiling, training, evaluation, and many other commands. It also features a Python interface. This allows for programmatic access to all of the utilities and scripts that come with the MLTK. So rather than running the profile command from the command line, you can run the profile Python API instead. And likewise for training and many of the other actions that you can do for model development. It also features Python, C++ Python wrappers. C++ Python wrappers allow for sharing code between the model training scripts and the actual embedded device. I'll get into more details on all of that in a bit. The MLTK also features reference models. These provide complete examples of how to actually generate and train the models that can later be executed on an embedded device. And then additionally, the MLTK comes with numerous example applications. These demonstrate how to load the machine learning models and execute on the embedded device. So now that we have an idea of what the MLTK is, why should we use it? What is it? What problems does it solve for us? Well, many times the model training logic can be spread across numerous different scripts, numerous different files. The MLTK allows for combining a lot of the logic that would go in for all these different training steps into a single Python script. It allows for combining stuff like the dataset generation and pre-processing, the model training scripts, the model evaluation and quantization. All these different tasks can be combined into just a single Python script. This can help to reduce the complexity and help make the model generation more reproducible and distributable. It's also very important that any data preprocessing used during training is also used on the embedded MCU. So anything you do to the model training samples during training has to also happen on the MCU. To help with this, the MLTK features something called C++ Python wrappers. These Python wrappers allow for sharing code between the model training scripts and the embedded device during inference. So the exact algorithms used during model training can also be used on the embedded device. I'll get into more details on that soon. It's also very critical that any pre-processing settings used during model training, any of the hyperparameters used for model training, are distributed with the machine learning model. The MLTK allows for embedding the pre-processing settings into the model file, into the TF-Lite model file. This ensures that the pre-processing settings and the machine learning model are effectively an atomic unit. You only have to distribute one file. You don't have to worry about distributing settings in a separate format along with the machine learning model itself. The MLTK allows for all of it to be encapsulated into just one single standard TF-Lite file. And I'll get into more details on that as well. There are also numerous different software libraries required to create a machine learning model and then execute it on the embedded MCU. The MLTK provides a seamless integration of many of the software libraries. It allows for integrating TensorFlow, TensorFlow Lite, TensorFlow Lite Micro, and the Gecko SDK. All these different software stacks can be, or the experience of using this can be consistent, and it can allow for model training and embedded runtime to be just a more consistent development experience. So now that we know what the MLTK is and what problems it can solve, what actually comes with the MLTK. probably one of the more useful features that comes with the MLTK is its model profiler. This provides lots of model runtime metrics such as memory usage, including the flash and the RAM that's required to run the model. It also provides other information such as the latency, or the amount of time it takes to do an inference, and then other stats such as the CPU cycles, the energy, accelerator cycles, and many other stats. The model profiler can either run with a simulator or on a physical device. So in a simulator, the model runs through a simulated environment. All of the metrics and the CPU cycles and all these different metrics are estimated using a hardware accelerator simulator. It also allows for running on the physical device. So the model's actually programmed to the physical device, it executes, and all the profiling information is then sent back to the MLTK for displaying in a nice, pretty format. The MLTK also features an audio feature generator, C++ Python wrapper. The audio feature generator allows for converting streaming microphone audio into spectrograms. And this is very useful because the algorithms, the C++ algorithms that run on the embedded MCU can be shared with the model training scripts. So the exact algorithms that run on the embedded MCU can be compiled for the PC, for the desktop computer, and execute on the desktop computer from just a Python environment. The MLTK also features numerous model generation scripts. It includes lots of utilities for data preprocessing and data set management, as well as model training, evaluation, quantization, many different common tasks that are required for model and machine learning model generation. It also features C++ example applications. There's many end-to-end examples of some of the more common machine learning use cases, including keyword spotting, as you just saw. There's image classification. There's a fingerprint reading example, and more to be added in the future. So the MLTK has lots of other utilities. There's, too many to add to just this one slide. Which is all thoroughly documented on its online documentation website. You can find the MLTK's documentation at siliconlabs.github.io/MLTK. It's all the documentation along with the MLTK source code is available on GitHub. You can find it at github.com/siliconlabs/MLTK. The MLTK also comes as a standard Python package. So using pip or conda, you can install the MLTK as it's just a standard package that's available on pi.org. And once again, the tutorial for this particular demo is also available in the Scilabs documentation. There are numerous tutorials. This happens to be one of them, and you can find that on the link provided. So yeah, I'll get into the models in a bit here. We'll go into more thorough detail about how the machine learning model works for this particular demo at the end. Let me just kind of blaze through some of the rest of the MLTK here, and we'll jump right into that. And having said that, let's talk about how the keyword spotting model was actually created. So let's talk about how the keyword spotting model was created using the MLTK. So first, a bit about how keyword spotting works in general. This is one implementation of it. There are numerous different ways of doing it, but the way it was done in this demo is you have your raw microphone audio coming from the microphone. That is being captured by the microphone, sent into the MG24, and then using the audio feature generator library, we're converting that audio signal into a spectrogram. Spectrogram is effectively a 2D grayscale image. It's you can think of it as like a signature of what the given audio looks like. That picture or spectrogram is then sent into a convolutional neural network or CNN, which classifies the spectrogram. Each keyword, left, right, up, down, has a certain picture, a certain look to it. And the convolutional neural network is able to detect the patterns of each keyword and hopefully provide a high probability of which keyword is in the audio. So once we do the post-processing, we assign a class ID to each keyword. So if the word left, then the output is 0, or right, the ultimate output of the post-processing step is 1. And that class ID is then sent to the application. So for this demo, that class ID is sent to the Bluetooth, and then the web page receives what the given class ID and knows how to drive the Pac-Man accordingly. A more thorough documentation for how keyword spotting is done is available on the MLTK website. There's a link down at the bottom here for that. So a major part of keyword spotting is converting the raw audio into a spectrogram. However, many different settings and algorithms are required to generate that spectrogram. And an important step here is the data pre-processing. So we're converting the raw audio into a spectrogram. We call that data pre-processing. That step has to be consistent between the model training scripts and the embedded device. And a divergence may cause the embedded machine learning model to see different data, which will reduce the accuracy. So put another way, if the spectrograms generated during model training are different than the spectrograms generated on the embedded device, then the model's gonna see different spectrograms and probably not be as accurate as you would like. So to help with this, the MLTK features an audio feature generated utility. And this allows for sharing code between the model training environment and the embedded device. So the key part of the audio feature generated utility is it converts raw audio signals into spectrograms. This utility, the audio feature generator, is provided as a Gecko SDK C++ library. So it's the utility that converts raw audio into a spectrogram. That code, those algorithms, come with the Gecko SDK, and they actually execute on the embedded device. That exact code is made accessible to the Python training scripts by wrapping it up with a Python wrapper. So we take all that code that comes with the Gecko SDK, we wrap it up in a Python wrapper, and then we can run those exact algorithms from our Python scripts. And this is very useful because then we can actually, during model training, we can generate the spectrograms using the exact code that runs on the embedded device. Additionally, we have libraries. There are many different settings required to generate a spectrogram. So there's lots and lots of settings to configure the audio feature generator library. These settings can actually be defined and configured in your model training Python scripts, and the MLTK will automatically insert these settings into the machine learning model. So all of this, the audio feature generator Python wrapper and the automatic insertion of the library settings, helps to ensure that the spectrograms generated during model training look the same as what is generated by the embedded MCU at runtime. So, as I said, the audio feature generator, the spectrograms, there are many different settings needed to create a spectrogram. You have the sample rate, you have the window size, the window step, upper band frequency. There's many different settings. To help get an idea of what to choose for each of these settings, the audio feature generator features an audio visualization utility, which allows for adjusting these settings and viewing the generated spectrogram at runtime. And it should also be noted that because of the Python wrapper, the exact source code that runs on the embedded MCU is used on the PC to generate the spectrogram. So this utility is available with a simple command line, MLTK view audio. When you run that command line, it'll pop open a utility that looks like this. So what you're looking at here is a spectrogram of the keyword left. So at the audio file, I just picked a I picked a data sample of somebody saying the keyword left.
Left.
So somebody said the keyword left, and we convert it into a spectrogram. And so that's a picture of the keyword left. And again, critical to note here that this spectrogram was generated using source code that's able to actually execute on the embedded device. I took that embedded source code, wrapped it up in a Python wrapper, and now I'm executing it on my PC. And it's generating the spectrogram you see here. So that's good. I can see the spectrograms that would ultimately be seen by the embedded MCU. You can see there's lots of different settings here. We can, for instance, we can enable or disable the noise reduction block, get an idea of what the noise reduction block does to these generated spectrogram. We can adjust the window size, the window step. So you can kind of see how the spectrogram changes as we adjust these settings, and it's updated in real time, which is handy. Another important thing to note is the spectrogram dimensions. So you can see this particular spectrogram is 32 by 99 pixels. So those are the dimensions of the spectrogram. Ideally, we would adjust these dimensions and make them as big as possible, because the larger we make them, the more resolution the image has, effectively. So the more resolution you have, the more details that are in the picture, and therefore hopefully the CNN can pick up those details and become more accurate with detecting the various keywords. So you can see when I adjusted the number of channels to 84, the detail of the image became greater. Unfortunately, we can't just blindly increase these dimensions as large as possible. The bigger you make the input image, the more processing that's required by the machine learning model. And ultimately, the greater the latency for doing an inference on the embedded device. And it's critical that we keep the latency as small as possible so that the game feels more responsive. Say the settings we chose here, the dimensions, took 500 milliseconds to execute. This utility allows for actually streaming the audio and getting a feel for how it would look to the embedded device. So if I enable the audio pipeline loop here, click the box, we can see the audio streaming across the buffer. So this is the raw audio is always being captured by the microphone. It's always coming in. There's no flow control. The machine learning model, or the MG24 and the audio feature generator, generates a spectrogram from the given audio that's in the buffer at the current time, takes that spectrogram and it sends it to the machine learning model. And if it takes 500 milliseconds to run the inference, then the next time you look at the audio, you're 500 milliseconds in the future. So this gives you an idea. You can see how it's the resolution is not great. It's very choppy. We're cropping a lot of the audio. Ideally, we would keep the processing to a minimum. We keep the inference latency low. One way of doing that is to just reduce the size of the spectrogram. So say I reduce the size to 68, for instance. The resolution goes down to the image, so there's not quite as much detail in the spectrogram, but the size is smaller. So hopefully, maybe the inference latency goes down to, say, maybe 100 milliseconds. So when we reduce the latency, you can see it streams across the audio buffer much smoother. So this will hopefully allow for the machine learning model to be more accurate, just because the audio is streaming across the audio buffer slower, because it takes less time to do one inference on the embedded device. So basically, this audio utility allows for, one, seeing how the settings affect the generated spectrogram, and two, it kind of gives an idea of what the audio looks like as it streams across the buffer. So again, we can reduce inference latency by reducing the size of the spectrogram. Another way of reducing the latency is to reduce the number of parameters in the actual machine learning model. So once again, latency is critical for in-game experience. And ideally, an inference should take less than 100 milliseconds. The longer, say it takes 1 second to do an inference, then that means when you say the word left, it's going to take more than a second to move that Pac-Man. It's going to take more than a second before the Pac-Man actually moves left. So we want to keep that inference as small as possible so we have a nice in-game experience. So ideally, when we're developing our machine learning model architecture, we'd be able to profile the model before we train it, and we spend the hours and days training the model. An ideal flow would be we create our model specification. We define all the different layers of the model, the number of filters, and just we define the model layout using Keras or TensorFlow like normal. We then build the model, and we generate a TF-Lite model file using just a few epochs and maybe a subset of the data set. More or less, we want to create our TF-Lite model file using dummy weights. That doesn't need to be fully trained at this point yet. We just want the TF-Lite model file. And then from there, we take that file and we program it to the embedded device, or we use a simulator, and we profile the model's execution. And then the profiling report will then spit out the inference latency. If the inference latent time is too high, then that means we need to go back to step one. We need to reduce the number of filters and layers in the model so that the inference time goes down. Once we have a model we like, then we can actually jump over to our model training scripts and fully train the model. So this whole process is made available with a simple command line on the MLTK. So we have MLTK profile and then your model. And this model can either be the name of the model or the previously generated TF-Lite file. We have this -- build option. This tells the MLTK to take your model and quickly build it using effectively dummy weights. We just want the TF-Lite file. We don't need the fully trained model. -- device means we actually program the TF-Lite file to the embedded device so we can profile it on the physical device. And then also we have -- accelerator, MVP. This just tells the model profiler to use the machine learning hardware accelerator optimized kernels, as opposed to the reference CNSys kernels that come with TensorFlow and Micro. So I've gone ahead and ran this command already. So you can see here, MLTK, and then the name of the model that I used. I built it. I just quickly, like using effectively dummy weights, I generated a TF-Lite model file. And then I used -- device, so I programmed it to the development board, and then I used our MVP accelerated kernels. That gets programmed to the MG24. It's profiled on the physical device, and then all the results are sent back to the command line here and printed out in a nice, pretty format. So the most important piece of information here is time. This particular model took 83.8 milliseconds. So that's good. That means this model should hopefully work in our demo. The profiling report also provides quite a bit of other useful information. The input shape, the data type, the output shape. It also provides the amount of flash that's required for the model. This is 46K. I should note this is effectively the size of the TF-Lite model file. It also provides the amount of RAM that's required, and that's the TF-Lite Micro's tensor arena size. So this one took about 91K. It provides that information about the number of operations required to do one inference. And something that's more useful here is the number of unsupported layers. So this will tell you if the given model is able to be fully accelerated on the hardware accelerator. If any layer is not supported, then this is a good indication that you need to go back and redefine your model architecture so that it can be fully take advantage of the hardware machine learning accelerator. I'd also like to note that the model profiler will work with any TF-Lite file. It doesn't have to be generated by the MLTK. Any TF-Lite file, quantized TF-Lite file, will work in the model profiler here. And one more note that you don't have to run this from the command line. The MLTK also comes with a standalone utility, a standalone executable that uses double-click, and it'll spit open a locally served web page. So you can run the model profiler entirely from just a single executable. All this information is available on the Scilab or the MLTK's documentation website. So now that we have our model architecture, we're confident that it's going to run fast enough for our application. the next thing we need to do is training. So model training can be very computationally expensive. It can take a very long time to train a model on a standard laptop, for instance. And many times this is because the CPU, not the GPU, is the bottleneck. This is many times because the data pre-processing is done on the CPU, and it can take longer to generate a batch of augmented training samples than it does to actually do the back propagation on the GPU. So we can improve training times if we can somehow break up the data augmentations and all the stuff that happens on the CPU across all the available CPUs. When we do this, we can further speed it up by adding more CPUs to the system. Many third-party vendors allow for renting cloud machines. So there's lots of vendors out there that allow you to rent their cloud machines, and they provide a wide range of different machines featuring one or more GPUs and 64, sometimes up to 128 or 256 CPU cores. And you can get these machines many times for less than $2 an hour. When the machines rent it, they typically provide SSH access to a Linux environment. And then once you have that SSH login, you can do whatever you want, like as if you were running locally in your own terminal. To aid the development of machine learning models, the MLTK comes with an SSH command. This allows for seamlessly training machine learning models on a remote machine. Once training completes, all the training output files are then automatically downloaded back to the local machine. Using just a simple command line, MLTK SSH train, then name your model, this will securely upload your model to the remote machine. The model will train using the MLTK and using the machine's many GPUs or CPUs and all its RAM, and hopefully quickly train on the remote machine. Once that finishes, all the output files are then automatically downloaded back to the local machine. So in this way, it's almost as if you train the model locally, but it quickly happened on a remote machine. And also, again, there's for more documentation about how this works on the MLTK's website. So once training completes, the MLTK will automatically evaluate the model. It will automatically provide class accuracies, it'll generate a confusion matrix, and many of the other metrics that are typically used for evaluating a standard machine learning classifier. However, many times it's also helpful to actually run the model on a physical device. This can help to account for the sensors capture of any of the pre-processing discrepancies that actually happen on a physical device. And more importantly, running on a physical device accounts for the actual latency that you would encounter on the MCU. So to help with this, the MLTK provides an audio classification utility. This allows for taking your trained keyword spotting model and running either on a local PC or actually programming to a development board. The audio classification utility also supports dumping the raw audio from the microphone, as well as dumping the generated spectrograms. So the spectrograms generated by the audio feature generator can be dumped from the embedded device. So you get an idea of what is actually being seen by the machine learning model. So this can be done, again, another simple command line, MLTK classify audio. I'll go ahead and run that right now. So we have the audio classifier. So you see, I'll go ahead and run it. So MLTK classify audio, the name of your model, and then -- device means I want to program it to the physical device. Again, if I didn't have this option, then it would just run on the local PC instead. And then I want to use the MVP hardware accelerated kernels as opposed to the CMSIS kernels that come with TensorFlow Lite Micro. And also we have -- verbose to just provide more verbose logging information. So right now the command is programming the audio classifier utility to the MG24 development board that I have locally connected. And it's also programming the TF-Lite model file that I trained, that I used for this demo. So once it's programmed, the app fires up, and then this, you're now looking at the serial output of the of the application running on the dev board. See, it provides lots of information about the model, the amount of runtime memory, and other information. It also spits out the audio feature generator settings. So remember, we had all these different settings necessary to generate a spectrogram. These settings get embedded into the TF-Lite model file. And then the device, the application on the embedded device, can read out these settings. So all these settings that you see here are actually configured in Python. They were embedded into the TF-Lite file. And then at runtime, the MCU can read those settings and configure the audio feature generator library accordingly. So the keywords that this model detects are left, right, up, down, stop, and go. And then there's an unknown class for anything else that's not one of the keywords. As the application runs, it reads in microphone audio, generates a spectrogram, runs through the keyword spotting model, machine learning model, and then the output of that model is just a list of probabilities. And that's what these probabilities, that's what these different columns are here. So this first column here represents this column here represents the word left. This column here is right, and so on. So each column is just one of the keywords that the model detects. And it should also be noted that the parentheses here is the total loop inference time. So to run one loop, it took 121 milliseconds there, took 127 milliseconds. So that's the total time it takes to generate the spectrogram and run the inference. So if I go down here to the bottom, we can see the real live streaming output from the classifier. So if I say a keyword, it should hopefully be detected here. So if I say left, right, up, down, stop, go. So you can see this is running in real time. The microphone audio is being captured on the dev board, spectrograms are being generated, and it's running through the machine learning model and then being spit out to the serial console and then displayed in my local PC terminal. And again, this was all done from just a simple command line. That's all I had to do to run this application and see how my machine learning model works using the audio classifier utility. So now that we have a machine learning model that we're feeling good about, it seems to be working well, it's time to actually deploy it to the device. So we have, let's just go over an overview of how this works. So the first thing, after training completes, after the model is fully trained, the MLTK will automatically quantize and convert the model to the TF-Lite model format. The TF-Lite model format is just the standard format used by TensorFlow and TensorFlow Micro. It uses something called a flat buffer, and this model format is programmed directly to the embedded MCU's flash. The TF-Lite model format is converted using the standard TF-Lite model converter. This comes standard with TensorFlow, and it's used to quantize the weights and the filters from float 32 to int8. int8 is a much better data format for embedded MCUs, and it's also something that the hardware accelerator can accelerate. It needs this data format to fully accelerate the machine learning model. Something else that automatically happens by the MLTK is the generated TF-Lite model file executes in the TF-Lite Micro's Python wrapper. So recall we had the audio feature generator Python wrapper. That was C++ code that is wrapped up in Python, and then we can execute it from our Python scripts. The same thing is happening for our TF-Lite Micro Python wrapper. So we take the TF-Lite Micro stack, the source code that's able to run on an embedded MCU, and we compile it for the PC, and we wrap it up in a Python wrapper. So that way we can run TF-Lite Micro from just standard Python environment. And this is useful because it allows us to determine the tensor arena size. So we take our TF-Lite model file, we run it through our TF-Lite Micro Python wrapper, and we can determine the amount of RAM that's required to run the machine learning model. And this is also useful because it allows us to verify if the TF-Lite can even fully execute on the MCU. So we can get the amount of RAM that's required, and we can determine if the TF-Lite file can even run from just our PC. We don't have to ever program it to the physical device. We can get all this information by just running a simple Python script on our computer. And also during this step, the audio feature generator settings, all the settings needed to generate a spectrogram are embedded into the TF-Lite model file as the metadata in the TF-Lite models. So all these settings used to generate the spectrogram are automatically inserted from Python into the TF-Lite model file, and then they can later be read by the MCU at runtime. This helps to ensure that the settings used during model training on the PC are the exact same settings that are used by the machine learning model on the MCU at runtime. There's further documentation about how all this works on the MLTK's website. So now that we have our TF-Lite model file, our quantized TF-Lite model file, it's time to actually run it in the application. The MLTK features a general purpose BLE audio classifier example app. This works very, very similar to the example app I just showed you, the audio classifier app. It continuously captures microphone audio and uses the audio feature generator to generate spectrograms. And then those spectrograms are sent to the machine learning model for classification. If any keywords are detected, the detected keyword is then written to the BLE GAT server as a notification. So it's effectively the same thing as you just saw, the audio classifier utility, except it has an additional BLE GAT server feature to it. And again, the audio feature generator is used to generate the spectrograms from the microphone audio. And more importantly, the settings are dynamically loaded from the TF-Lite model file. So all the spectrogram settings are dynamically loaded from the settings embedded into the TF-Lite model. And then once again, we have TF-Lite micro, which is used for inference. The TF-Lite model file, the trained model file, is loaded from the MCU's embedded flash. And then custom kernels are custom kernels that use the machine learning hardware accelerator are used by the TF-Lite micro stack. There's further details about this example application on the MLTK's website. So to wrap it all up here, we have the MLTK. The MLTK helps to bridge the gap between model training and embedded execution. It features Python wrappers, which allow for sharing code between the model training scripts and the embedded runtime environment. And it also allows for embedding training hyperparameters into the TF-Lite model file so that the MCU can read those settings at runtime. The MLTK features a rich set of tools to aid the development of machine learning models. I'd also like to stress here that all the tools that come with the MLTK are optional and they may be used independently. So you can use the model profiler all by itself. You don't need to, the model does not need to be trained by the MLTK to use the model profiler. The model profiler will work with a standalone TF-Lite model file. And this is true for many of the other tools that come with the MLTK. And finally, MLTK offers end-to-end examples of some of the more common machine learning use cases. It demonstrates how to develop the machine learning models and then how to actually run those models on an embedded MCU. Well, so with that, I thank you for your time, and I'd like to once again mention that all the documentation for the MLTK is available on our website, Silicon Labs, github.io/MLTK. And now let's open it up to some Q&A.
Well, thank you, Dan, for sharing details on this powerful tool, MLTK tool, and for showing the demos, live demos. That's super powerful. Yeah, we have several questions from the audience, kind of related to your last bullet on your summary slide. Bin is asking, have you considered other architectures besides CNN? Because kind of he thinks that people use CNN as a hammer and forget about kind of other type of things. Yeah. What about kind of other networks, other type of features you can run using the tool on the Silicon Labs hardware?
Yeah. So actually, we have been looking. So yeah, CNN is one way of doing it, and effectively you need to generate a spectrogram to do that. Another way we've been looking into is using 1D convolutional neural networks. So you just take the raw audio, you pass that through 1D convolutional filters, which you use that to effectively generate the spectrogram instead of doing traditional DSP like the audio feature generator use. So to answer your question, yes, we have looked into other ways. We're still looking at how we can actually fully integrate that and create another demo out of it.
Yeah, thank you, Dan. There's a question from Ari on training. He's wondering how many spoken examples of keyword were needed to train the Pac-Man command model, the one you showed during the demo. What was your kind of data size for training data set?
So all of these details, once again, I'd like to mention, are available on the MLTK's website. This just used the standard Google speech commands data set, and each class had about 3,000 samples. So honestly, that's probably the biggest downfall of this demo is the data set is just 3,000 is just too small. You really need 10,000 or more to make a robust demo or to make a robust model. So this demo works, but it could be better if we just had a larger data set. But to directly answer your question, about 3,000 a class, just based on the Google speech commands data set.
And that gives you enough accuracy kind of for the demo you showed today, right?
Yeah.
Probably.
Yeah.
Okay.
Could be better, but yeah, that works.
There is a question from YM. Last year, NVIDIA made the whole Pac-Man as a gun. Did you think to integrate this and make a one big model with audio as input?
Yeah. The MG24 runs at 80 megahertz. So there's kind of an upper limit. It only has 256K of RAM. So there's kind of an upper limit to the big models that we can run on this particular piece of silicon. No, we haven't tried anything like GANs or anything fancy like that, just due to the compute resources available to the MG24. The MG24 is really geared towards low power, low footprint applications.
And just to follow on this question, there was an earlier question on how much resources like memory and processing is available on this particular board, and how much of these resources is taken by the OS, by the Bluetooth and other type of resources you need to run the chip.
So the MG24 board that I use today features 256K of RAM and 1.5 megabytes of flash. The machine learning model itself used approximately 91K of RAM for the tensor arena. And then the stack and everything else, it topped out at about, we'll say like 120K of RAM. So less than half the RAM was required for this particular demo. And then the flash was, I think the flash image is like 500K.
Okay. There is a follow-on question from David on the training side of things. He is saying, given the high number of samples required to train a model, you mentioned like over 3,000, will it be possible to have some kind of on-device fine-tuning? Let's say you have a model with less trained with less data sets, and can you just fine-tune it afterwards?
Like on-device training. The
Yeah.
MG24 does not support on-device training, unfortunately. The model needs to be trained offline. But there are other tricks that can account for small data sets or imbalanced data sets. The MLTK allows for automatically balancing the data set. This is using a standard formula for adding class weights to each of your samples. So during model training, it looks almost as if the classes are balanced. There's an equal amount of samples for each class. That's in the tutorial as well, the details for that.
Yeah, and there is kind of a similar question from Mark on transformers. Obviously, transformers are becoming more popular. Can you run transformers on this board? I assume the answer will be. Well,
I don't. As far as I've seen, transformers aren't directly supported by TFLang Micro just yet. I think if you want to, it can be done if you want to get really, really into the details of how it works. But as it stands right now, at least from what I've seen in the latest, you can't take a transformer model and directly run that in TFLang Micro just yet, due to the lack of some of the kernels aren't directly supported just yet. So yeah, that's something we have looked at. Transformers tend to use a considerable amount of RAM. So I don't think transformers are quite there yet. I think the scientific community needs to kind of work and find a way to reduce the RAM a bit more before they'll work on the MG24's 256K RAM.
Yeah. Okay, I think we're running out of time.
Well, there's one more that said the probabilities for unknowns greater than 100. That's because the output of the model is scaled from 0 to 256. Or yeah, so the highest 255 would be the maximum value, and that's why the maximum value is 255, not 100. Okay. So the range is from 0 to 255.
Okay, thank you then. So I would like to thank the sponsors and tinyML strategic partner companies, including Silicon Labs again. Thank you. And one by one, the executive sponsors are ARM, HMPulse, Qualcomm, Sentient. The platinum partners are DeepLight, ClickerTech, Reality AI, and Renaissance, and Sony Semiconductors. And the gold strategic partners are Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SensiML, ST Microelectronics, Synaptics, Synsense, and we have many silver partners as well, including Silicon Labs. Thank you again. We'll see you next week at Pete Warden's presentation next Tuesday, same time, 8 a.m. And thank you for joining, and we'll see you next week. And thank you, Dan, for very informative and hands-on presentation and answering many questions. Thank you.